Hey everyone, welcome to the start of our Year 10 linear relationships section of this topic. Now, this video is going to be reintroducing just some concepts we've already covered in the past and talking about new ways to solve these types of problems, particularly those involved with finding equations of lines. Now, as I've said before, this is building on things we've already done before. So this video assumes that you will have some knowledge of what a gradient is of a line, what an intercept is, what the equation of a line generally looks like. And we're just going to be adding on to this with some new ideas. So if anything here is unfamiliar, please go back and watch the videos we covered in the Year 8 or Year 9 topic of linear relationships. Now, jumping straight in, we want to do some practice questions. Now, the first one's going to be on the gradient of a line, and the next two are going to be slowly building up to equations of a line with greater difficulty as we go. Now, we want to find the line, or the gradient of a line, joining the points -3 and 5, -2. Now, I've drawn these on this plane here, and in school you'll be given a lot of different fancy formulas for how to solve this, and I'm going to get to those, but I want to first just get you thinking about the gradient in the easiest possible way. Now, we defined a gradient, m, as the ratio between how much a line rises and falls. Rises and runs along. So we defined this gradient as rise over run. So essentially how much it changes in the y-axis. So we'll call this a change in y divided by a change in x. Okay, so let's just take a moment to consider this. Never mind. So, let's look at, for example, starting at this point, what's been the change in y to get down to here, as well as the change in x. And dividing that change in y by the change in x will give us the gradient. Now, here we're starting at 8 on the y-axis, and we end up dropping down to -2. So going from 8 all the way down to -2, how many units have we gone down? Well, we've gone down 8 getting from 8 to 0, and then another 2 getting down to -2. So our gradient, our rise is going to be 10. Now, you may be thinking to yourself, well, we're not rising here, we actually fall from 8 to -2. So, and also, if you remember the idea of a gradient and how slopes look, if our line goes down looking from left to right, our gradient is going to be negative. But I just want you thinking about this as this line is falling. It's not rising, it's falling. So it is rising from 8 to -2, -10 units. So the direction here is important. We're not going, our y isn't increasing, it is falling. So the 10 units I've counted here are going to be negative. And now I want to find my run. So how far along have I gone in the x values? So I start at -3 and I make my way up to, let's do this again. I start at -3 and I make my way over to +5. So here I'm going in the positive x direction. So I've gone from -3 to 0, that takes me 3 units along, and another 5 units from 0 over to x being 5. So my total distance here, I've gone 3 and an additional 5. So I have gone 8 units. I've run along 8 units from this point to this point. Now my gradient is just going to be my rise over my run. So my gradient m is going to be negative 10 over 8, which we can simplify to negative 5 over 4. Now you're probably thinking, well, wait a minute, the equation I've been given in my textbook is my m equals y2 minus y1 over x2 minus x1. This is another way you'll be presented with the gradient. So let's actually look at what this minusing actually entails. Because, well, what this minusing, for example, is telling us. That's just telling us the difference between this y and this y. Or the other way around. The difference between this negative 2 and my 8. And the difference in x, my x2 minus x1, is just the difference between this thing here and this thing over here. And when we actually do that, when we subtract one from the other, we're going to get these values in. So let's just consider that. So let's do this exact same question, just in another way. And here we're going to consider these points as x1, y1, and we're going to call these x2, y2. And we're going to see if we're going to get the exact same answer. So we know from our other formula we've been given in our textbooks, you'll see this a lot. We also touched on this from last year's content. I want to subtract y1 from y2. So I'm going to take y2, that's negative 2, and from that I'm going to subtract positive 8. So y2 minus y1, I get minus 2 minus 8. x2 minus x1, I get 5 minus 3. Minus 3. So let's clean this up a little bit. Now this is like saying negative 2 minus 8 over 5 minus 3 is the same as, the double negative is the same as an addition. So I'm going to get minus 2 minus 8 gives me negative 10, and 5 plus 3 gives me 8. So I get the exact same thing as before. Now these are just two ways to think about this, but my first method that I did was really just a matter of finding the difference between my two pink highlighter numbers, between 8 and negative 2. And we did that by subtracting one from the other. Now I did, for example, minus 2 minus 8. Or I could have done 8 minus 2, and then when I did the same thing with my x's, I still would have gotten a negative. So I still would have gotten this negative sign of my gradient here. So the way we go through these questions end up being exactly the same. Whether you use this initial formula that we learnt, defining the gradient as rise over run, and just finding the distances between the two different y values and the x values, or this formula, this newer formula you would have learnt last year. So that's how we can think of the gradient. Now let's move on to another question. Now we're going to be looking at equations of lines. And we're using very similar ideas here. Now I'm going from here, the point 0, 1, up to the point here of 4, 13. Okay, so joining these two dots. Now I want to find the equation of this line now. So we need to consider our equation of a line formula. And that's going to be a bit of revision from before. my y equals, or the general equation of these lines is going to be mx plus b, or some people use c instead of b, but what these essentially are the gradient is m, we talked about that before, and the b is the y-intercept. So where the line crosses the y-axis, where it touches it for the first and only time with a line. Now, okay, I want to find my gradient first, and then my y-intercept, and then just substitute each of those into my formula up here. So let's actually start with the y-intercept, because that's a little bit easier. Well, my y-intercept, we define that as where on the y-axis the line passes. And we can see here, this line is passing through the point 0, 1. And if we remember from last year, when x equals 0, we get our y-intercept. Or we can just look at it visually and say, okay, I can clearly see this line is passing through 1 on the y-axis when it first touches that y-axis. So I can just substitute that straight in. I can say, okay, my b equals to 1. My y-intercept is 1. So we're getting a little bit closer. Let's write that into my equation. So y equals mx plus 1. And now I need to find what my gradient is. I need to find this guy over here. So I can do this in a couple of ways. But I'm going to do it here by considering how far my line increases in the y from here to up here, and then how much it increases in the x direction as well. So I'm starting at 1 in the y, and I'm going up to 13. So I want to see how many units have I actually traveled. Well, the difference between 13 and 1, or y2 minus y1, if we think of this as y2 and this one as y1, that's going to give me 12. So looking at this visually, or using my y2 minus y1 over x2 minus x1, I still get 12 both times. And now I need to just find the difference in the x values. So from 0 on the x here up to 4. Or I can think of this as x2 and x1. Okay, so finding that difference, I start at 4 and I make, I start at 0 and I make my way over to 4. So I've traveled a total of 4 units in the x direction. So that's my change in x. And also x2 minus x1, 4 minus 0, also gives me 4 as an answer. So no matter which way I go about this, I always get the same gradient. And we can also do this if I made, for example, these points down here x2, y2, and I made these up here x1, y1, and subtracted it. We would get to the same answer. So there's a bunch of different ways you can go about these types of questions. So let's actually just show my working out here. My gradient is y2 minus y1 over x2 minus x1. And we said that was 13 minus 1 over 4 minus 0. And that gives me 12 over 4, or 3, as my gradient. So now I have a value of m that I can substitute into here. So therefore, the equation of my line, the final equation of my line, is going to be y equals, instead of my m, my gradient, I'm substituting in 3. I get mx plus my y-intercept, which my b here we found is going to be 1. Now, let's do one more question. and this is going to be something very new to us. We want to find the equation of a line, but we're only given 2 points here. We're given the point 311, and we're given the point 67. We want to find the equation of this line, and all we know about it is that it's getting connected to 2 points. Now, there's a couple of different ways we can go about this question, and I'm going to run through both of the methods here. Now, this first method is going to introduce us to a new formula. Now, I'm going to do a little bit of explaining now and deriving this formula. So if that interests you, if you want to see why this works and that it's not just some arbitrary formula, you can watch this. If not, you can skip ahead to when we actually use this if you just want a quick revision of how we use this actual formula. So my first method is going to be using the equation, one that you may have seen in your textbooks, but whether you know how it works or don't, I'm going to go through this now and actually derive this formula. What the hell is this thing here? Well, we need to first consider a common fact we know about lines. And that is that no matter where we are on a line, right? If we have the points here, for example, A, B, C, these points are what we call collinear. So A, B, C are collinear. What does this mean? It means they all lie on the same line. They are points sharing a line. So something like that is actually very important when we consider trying to derive or make sense of this formula. And there's a bunch of different ways this is written, but we want to have a think about something to do with gradients of points that lie on a line. Now, the really neat thing about lines is that all the way through on a line, we have a constant gradient. We have a constant slope that doesn't change. So, for example, if I wanted to calculate the slope between the points A and B, that would be the same as the slope between B and C. And that would also be the same as the slope between A and C. So no matter which way we go about this, which slopes we're considering, whether it's the slope of joining A and B, whether it's the slope of B and C, whether it's the slope of A and C, the gradient is always constant. So let's give these points a name. So point A, let's say this is x1, y1. Let's say B is x2, y2. And let's just say C is just some arbitrary x, y here. We want to understand what is common with all of these gradients. Well, we just talked about that these are exactly the same. So, for example, I can make a claim that the gradient of joining the points A to B is going to be equal to the gradient, for example, of A and C. Now, let's write that. Let's write that in full words. So the gradient of AC. Okay, these two gradients are equal. Why do we know that? Because on a line, the gradient is always constant. We always have this constant slope here. And what we've just made a claim is that, well, the gradient here from A to B is identical to this gradient AC. You can graph out a line and try this same thing as well, but what that basically tells us is that the rise over the run of AB is going to be equal to the rise over run of AC, because that's just what the gradient is. So that means that, okay, the M of AB, the gradient of AB, the rise over run of AB, is going to be equal to the rise over run, M, of AC. Now, how can we actually express the gradient of AB? Okay, well, we can write that as y2, whoops, let's do a different color. That means we can write that as y2 minus y1 over x2 minus x1. That's an expression for the gradient. So, y2 minus y1 over x2 minus x1 is equal to the gradient of AC. So that here would be my y, the difference between y and y1, and the difference between x over the difference between x and x1. So that is going to be equal to y minus y1 over x minus x1. Okay, so this is what we have so far from the conceptual ideas we know about lines and linear relationships. Now, I want to actually just first bring your attention to the formula we wrote out up here. What's different here? Well, my y minus y1 and x minus x1 are on different sides, and my gradient, any gradient, because all gradients are the same, is expressed as m. So this thing here, y2 minus y1 over x2 minus x1, we can just write that as m, because that is just some gradient of the line. And we have y minus y1 over x minus x1. But here, if we scroll back up to our equation, my y minus y1 is the subject of the equation. It is on its own, and the x minus x1 is next to the m, or multiplying by the m. That should hopefully give you a bit of a hint as to what the next step will be. Now, if we wanted to make y minus y1 the subject of the equation, we're going to multiply both sides by x minus x1. So because this is saying y minus y1 divided by x minus x1 equals to m, if I wanted to rearrange this equation, I can just multiply by x minus x1 to both sides to undo this division on the right hand side. So I'm going to multiply this by x minus x1. And what do I get here? Well, I end up with m multiplied, or outside of x minus x1, equals to y minus y1. And this thing here is identical to the formula we defined up here, the one you're given in your textbook for, and that's what we're using for this method 1. Okay. So if you stuck through that and that was useful to you, thank you for that. I appreciate you sticking around. If you just wanted to skip to, okay, let's actually use this formula, we're about to do that just now. So let's consider our 2 points here. We had, so for method 1, we had the points 3, 11, and 6, 7. Okay. Now, let's just find the gradient of these 2 points. So, my gradient m equals y2 minus y1 over x2 minus x1. So let's call this y1, y2, x1, and that's x2, y2. Beautiful. And remember, the order here matters. So we can't, for example, subtract y1 from y2, but then subtract x2 from x1. Wherever we choose to start, we have to minus in that same direction. So if we're doing here, for example, y2 minus y1, 7 minus 11, we have to subtract x1 from x2. So we have to do, for example, here 6 minus 3. We can't do 3 minus 6. The order here matters. So 7 minus 11 is going to give me minus 4. And 6 minus 3 gives me 2. Just gives me 3. And now, so that gradient, just to reiterate the idea we defined before, that gradient is going to be equal to any other gradient with some arbitrary point y and its difference between some y1 and x, some arbitrary point x minus x1. And we get our formula, y minus y1 equals to m x minus x1. And now we have a value of m, so we can substitute that in here. So we have negative 4 on 3. Okay, and then now I just want to substitute in my points. So I can, interestingly enough, can either substitute in this one and this one, or this one and this one. I will get the same answer. But let's just do it with x1 and y1, because that's what we defined here. So I'm going to do y, and instead of y1, I'm going to put in, I think it was 11 equals to minus 4 on 3, x minus 3. Okay, and now I just want to come up with an expression for this equation here. So I'm going to get, just check if I've done the right points, 3 and 11. So I'm going to get y minus 11 equals to, expanding these brackets here, I get minus 4 on 3x, and minus 4 on 3 times minus 3 is going to give me 4. And I just want to rearrange the equation to make y the subject. So I'm going to add 11 to both sides here. And I wind up with y equals to minus 4 over 3x plus 15. That is the equation of my line. Now, just for fun, let's just, for example, in these, because the gradient is equal all the way through. So in theory, this should also work for the points 6 and 7 here. So let's just do that to test it out. Let's check for 6 and 7. Okay, so my equation now is going to be y minus, I'm going to try 7 now instead, equals to negative 4 on 3 x minus 6. Okay, so I get y minus 7 on this side. I still get negative 4 on 3x. Now multiplying negative 4 on 3 by negative 6 is going to give me positive 8. And to make y the subject here, I'm going to add 7 to both sides. So y is going to equal minus 4 on 3x plus 15. And I get the exact same thing. Now, why does this work? Well, it works because of this thing that we defined up here. It works because the gradient is equal all the way through. So whatever we choose right at the end, whether it's x1, y1 or x2, y2, or any other point, we're always going to get the same equation because these points are collinear. They lie on the same line. So that means that any point that I substitute into my equation, or into my formula that I defined down here, I'm going to get the same equation of that line. Okay, now I'm going to do one more different method. If you're satisfied with the one we just did, cool. I'm just giving you the option so you can use another one if this one is a little bit confusing for you. So we still have the points 3, 11 and 6, 7. Okay, what we're going to do now is we can still find the gradient, but we're going to use one of the other points to come up with an equation. And I'm going to show you how in just a second. So we can solve for the gradient in the same way. So 7 minus 11 over 6 minus 3, and we get the same negative 4 over 3. Another way we can do this is we can say, all right, I know that my equation of a line of all lines is y equals mx plus b. And in this case, my m is going to be negative 4 on 3 plus b. And now it's just a matter of finding this b here. Now, if you remember what we talked about in previous videos, or just from your previous studies, any point that lies on a line, so 3, 11 and 6, 7, both of these points, when I substitute them in, they satisfy this equation. They make the equation true. Or in other words, when we substitute them in, the left-hand side is going to equal the right-hand side. So I can substitute in the x and y values of either 3, 11 or 6, 7, and it's going to give me the same b and therefore the same equation. Why? Because both those points lie on the line. Now let's try this for both points. So what we're going to do here is we're going to check for 3 and 11. Okay, so I'm going to substitute my 11 in for the y and my 3 for the x. So my y here is 11 equals negative 4 on 3 multiplied by my x, which is 3 here, plus b. Okay, so I still get 11 here. When I multiply negative 4 over 3 by 3, I get negative 4 plus b. And then solving the equation, I'm adding 4 to both sides, which leaves me with a y-intercept, or a b, of 15. And look at that, that number 15 ends up being the y-intercept. If we look at this as y equals to mx plus b, my b is 15, the value that I confirmed down the bottom here. And this will work for the other point as well. If we were to check for 6 and 7, I'm going to get 7 in place of my y equals negative 4 on 3 multiplied by 6 plus b. Negative 4 on 3 multiplied by 6 gives me negative 8. And I can add 8 to each side. And that's going to give me b on its own on the right equals to 15. So it works this way as well. Now, I know I've exposed you guys to a lot of different things, a lot of different ways of thinking about this, but the idea is always the same. The reason it always works is because these points are collinear. If we go back to the thing I drew up here, all of these points lie on the line, as I saw up here. And we're using the fact that the gradient is equal all the time. That allowed us to use this formula that I spent a while deriving. But we also used method 2. It worked in the same way because these points are on the line. If they're on the line, they satisfy the equation. We can use it to find the y-intercept. We can approach these in a number of different ways, but that's enough for today's lesson. I know we've gone on for a very long time, but this is how we can start to attempt some trickier questions which require us to find the equation of a line when the only information we're given are 2 random points that lie on the line. Thank you so much for joining me, and I'll see you in the next video.